After t seconds, the displacement x centimetres of a small mass attached to a spring oscillates about a fixed point O according to the differential equation d2x dt squared is negative pi squared x. So you should recognise this as simple harmonic motion. The acceleration is equal to negative n squared x. We're told the initial velocity is 8 pi centimetres per second and the initial displacement is 0. So if it starts at the middle of the oscillation and it's heading that way, then we usually base it on a sine. So we can say that x is going to be a sine nt. Now, the n we can see from here is pi, so x is going to be a sine pi t. So we need to work out what the amplitude is. Now, we know that the velocity you get from differentiating the displacement. So that's going to be a pi cos pi t. And the maximum velocity happens in the middle with SHM. So in other words, this is the maximum velocity at the beginning here. And we're told it's 8 pi. And that implies that A is equal to 8. So I'm going to say that x is 8 sine pi t. We want to calculate the distance the mass travels during the first 5 seconds. Well, there's lots of ways that we could go about that, but probably the easiest, when we've got a calculator assumed, is to do the integral from 0 to 5 of the modulus of v dt. So that's going to be the integral from 0 to 5, and going back to here, we know that a is 8 pi cos pi t in modulus dt. So I just paused and typed that into the calculator, and I get 124.1, and we know that that's in centimetres. Actually, I just spotted there that I've got the calculator in degree mode, so I need to re-evaluate that in radian mode, and it's actually 80 exactly. So 80 centimetres. Always be careful and always check, as I did. Okay, so the differential equation d2x dt squared equals negative pi squared x assumes that the amplitude of oscillation A is a constant over time. Now assume that friction reduces the amplitude of the oscillation. According to the equation, dA dt is negative 0.4 A. Also assume that A0 is 8 centimetres. Determine the function A of t that gives the amplitude of the mass. In other words, we want to solve this differential equation. So separating, we get dA over A is equal to the integral of negative 0.4 dt. So log mod A is equal to negative 0.4 t plus a constant. So that means that A is equal to e to the negative 0.4 t plus a constant, and using our index laws here, we can say that that's be to the negative 0.4 t. Now we know that when t is 0, a is 8, so 8 is going to be, if e is 0, this side is just going to be b, so b is 8, and therefore A is equal to 8 e to the negative 0.4 t. As time passes, the amplitude continues to decrease to the point at which the small mass appears to stop oscillating. Determine correct to the nearest 0.1 seconds, or 1 decimal place, how long it takes for the small mass to appear to stop oscillating. So what we want is 8e to the negative 0.4 t to be equal to 0.01. So we just need to solve that. So I just paused the video and did that, and we can see 16.71. Now we're asked to give this to 1 decimal place, but this is important. If we round that to 16.7, it won't have reached here, so it will still appear to move. So we're going to say t equals 16.8 seconds to appear to stop moving.